Okay, I see people joining. Perfect. Okay, so I guess we can start. So hello everyone and welcome. Thank you for joining us today, students, professors, researchers, and those of you who are not from the academic community but are still interested in optimization and Python. My name is Mateo Gallia. I'm the academic program coordinator here at GAMS, and I'm very excited for today's session where we will explore GAMSPy and how it's bridging the worlds of optimization, Python, and data science. For those of you who don't know us, GAMS as a company has a very long and very proud history of both supporting and collaborating with academia all over the world. And today's webinar is all about how we can empower your research and your teaching with GAMSPy. So joining me today to guide you through the technical presentation are my colleagues, Vijay, who's an operations research analyst here at GAMS, and Muhammet, who's a software engineer here at GAMS and the main developer of GAMSPy. So we really have a stellar team with us today. So we're going to kick things off with a quick overview of the agenda for today's webinar. So if we can start the slides. Perfect. We go to the next one, which is the agenda. Perfect. So here's a look at what we have planned for you today. We will begin with a quick introduction and briefly talk about GAMS to set the stage. And then we will dive into GAMSPy and what it is all about. Then the centerpiece of our session will be a live demonstration on how to build an optimization model from scratch. In this case, it will be the classic transport problem. And we'll show you just how intuitive it is to work with GAMSPy and how powerful of a tool it can be. After the demo, we will explore slightly more advanced topics, like how to build an interactive web application for your model and how to integrate machine learning techniques. And then we will try to make the case for why GAMSPy, among so many other optimization tools, why we think that you should definitely give it a try. And for the final part, we will briefly discuss our academic program and other valuable resources that you as academics can access for free. And finally, we will wrap things up with a Q&A session. So also let me just say that if you have any questions during the webinar, you can just put them on the chat. They will be visible only to us panelists, and we will try to answer them in the moment. Or if they are interesting for everyone, we might leave them for the Q&A. This webinar is being recorded, so you will be able to watch it afterwards again if you want, and it will also probably be posted on our YouTube channel. So now for the technical and the interesting part of the webinar, I will hand it over to my colleague, Vijay.
Thank you. Thanks a lot, Mateo, for the introduction. Good morning, good afternoon, and good evening, everyone. And without further ado, let's get right into it. And let me try to motivate why we require GAMSPy in the first place. Yeah. And when it comes to solving real-world problems, it's not about just the model itself. We have to deal with all the messy details which comes with real world data. So we have to worry about the data cleaning. We need to manipulate the data in certain ways, and then also figure out how to visualize it well. This could be a challenging task, and most often leads to this optimization pipeline, where the data input pre-processing can be done in Microsoft Excel. Then the optimization model itself can be done, let's say, in GAMS. Then the post-processing and visualization can be done in a separate environment, for example, Python or R. So let's be honest, data manipulation, pre-processing, and post-processing can be a time-consuming and a tedious task, especially when it comes to a domain-specific modeling language such as GAMS. And this brings us to Python. As we all know, Python has become this one-stop solution, be it pre-processing, post-processing, or visualization. We can do all that in Python. It offers these vast array of packages to handle all these tasks and is often a shared language in a organization spanning group. Now, this could introduce a bottleneck which we want to when we want to communicate between Python and a modeling specific language such as GAMS. And this is where GAMSPy come into the picture. It provides a comfortable and efficient way of modeling the optimization problem in Python. In simple terms, we can now have everything within one environment. But before we introduce GAMSPy, let us first talk about what is GAMS. GAMS stands for General Algebraic Modeling System. It has been in active development since 1987. What GAMS allows us to do is define mathematical models like we're writing on paper. For example, as you can see, we have defined a transportation problem within GAMS, similar to how we would write the algebraic notation or the algebraic model for the problem on paper. So we have the parameters and variables defined over sets, and the constraints are written in a way that closely resembles to the algebraic notation. But what about the data? Well, GAMS allows us to write completely abstract models. That means it is data agnostic. And when it comes to actually solving the model, all we have to do is just import the data and execute the solve statement, and which is then generates the model. And this is the GAMS philosophy. Tight syntax makes us write better models. In a nutshell, GAMS is a stable and efficient algebraic modeling language, which is being actively developed since 1987. The data itself is held in GAMS data structure, which makes it fast and ready for large and even like very large models. With that said, we can now introduce GAMSPy. GAMSPy is also a algebraic modeling language, but now we can write our models in Python. It brings the same goodies from GAMS as it is using GAMS in the background. And this is where the magic of Python also shines. We can utilize third-party libraries like NumPy and Pandas for convenience and efficient use of data structures. With the help of GAMSPy, we can now have the entire pipeline in Python, which really streamlines the process. In order to demonstrate this, let's consider the transportation problem as an example. I'll give a brief introduction about the transportation problem. The problem contains some suppliers, in our case, the canning plants, specifically at Seattle and San Diego, and some markets, namely at New York, Chicago, and Topeka. The problem is to satisfy the demands at these markets while respecting the capacities at the plants and finding the optimal number of shipments that minimizes the total transportation cost. So here we are on the left, we have our production sites, and on the right, we have our markets, and we have connections between plants and the markets with the distance written along these arrows. For a more formal definition of the problem, here is the mathematical model formulation. We have two indices, which are canning plants as I and the markets as J. Our decision variables are Xij, that is the number of cases to ship from plant I to market J. Then we have some data. First, Cij, that is the transport cost per case to ship from plant I to market J. Then AI, which is the production capacity of plant I, and BJ, which is the demand of market J. Our objective is to minimize the total transportation cost, which is the sum over I and J of the product of the transportation cost and the amount of commodity to be shipped from the market I, from the plant I to market J. Then we have some constraints, namely that we cannot ship more from plant I than the total production capacity of the plant. We must ship enough to market J to satisfy the demand at the market. We also know that our number of cases to be shipped from plant I to market J must be positive. That is, we do not want to ship from a market back to the plant. Now let's see how this mathematical notation of the model translates into a GAMSPy model. And for that, we can jump into the Jupyter notebook. And by the way, you can find this notebook and a couple of more examples in the official documentation. We can also provide all the links at the end of the presentation. I hope you can see the Jupyter notebook.
Yeah.
And we first start with the description of the problem, where we define all the things which I have just mentioned. Then we start with installing the dependencies. And if you want to run this on a Google Colab notebook, you might have to, or you have to run this cell. But since I already have GAMSPy installed on my environment, I don't have to run this. So the next cell, uh, we import like all the necessary classes we require for building the model, as we usually do in any Python script. Once we have once I run this, I'll have all my necessary classes. And then a start of any GAMSPy model happens with defining the container. So you can take the container as a centralized hub where all your essential data, your symbols, yeah, your sets and parameters and other symbols would be residing. And this gives a proper structure or a clear structure to your optimization problem. Once we have defined the container, we can start with defining the sets. Now we can do this by just using the class set and specifying where this set would live. In our case, it'll be the container M. We can give it a name, I, and a meaningful description, let's say plants. And if I run this, you will see we can quickly check the name of these variables by just using the property name on these variables. And you can see it's I and J. You can also define a set without specifying the name and description. If I just run this, you can see GAMSPy would generate a name for the dummy symbol, but it is highly recommended to use to add a name to your sets because it'll be beneficial when you want to retrieve the symbol again from the container. And you can do that by just specifying container and then using, for example, um, M and then specifying the name of the symbol. Next, we can define the parameters. First, we define the parameter A, which is the supply. And here we mentioned the domain. And since we want to have the supply for each plant, the domain would be I, which is a set of plants. And again, we give a meaningful description and we specify where the parameter would live. Similarly, we can define the parameter B, which is the demand for each market. And in this case, the domain would be J, because that's the set of markets. Again, we give a meaningful description. And then similarly for the parameter C, which is our transportation cost per unit of shipment between plant I and market J. And because it involves both the entities, the domain now would be a list of set I and J. Next, let me run this cell. Yeah. Next, we'll define a variable. And for this model, we just require one variable, which is X. Again, we specify where the variable would live. In our case, it's the container M. We give it a name. And the domain would be, again, I and J, because we want to capture the amount of commodity to ship from plant I to market J. The type in this case would be positive because again, we don't want to ship from the market J back to the plant I. Then we can define our equations. In GAMSPy, we first have to declare the equation objects. In our case, it'll be the supply equation and the demand equation. And for that, again, similar to other symbols, we mentioned where these constraints would live or the equations would live. Uh, that is the container M. We give it a name. And the supply constraint will be applicable on the domain I, which is the set of plants, and we give a meaningful description. Similarly, we declare the demand equation, which again lives in the container M. We give it a name and the domain J, because this time this uh, equation would be applicable on the set of markets. And now we can actually define the equation and how what it should do. So for the supply constraint, we want to restrict that we cannot supply more than the capacity at each market I, at each plant I. So basically, we want to sum over the amount of commodity to be shipped for every market, and that should be less than the capacity at for each plant I. Let's go ahead and run that. And similarly, for the demand constraint as well, we want to make sure that the demand at each market J must be met. So we have to ship at least the demand at each market J, and this captures and this expression captures that constraint. We can quickly verify what we have defined in the demand constraint by just you looking at the LaTeX representation by using this convenience method LaTeX wrapper, and this generates this LaTeX representation, and you can quickly see, okay, this is what we wanted to implement, and this will be this can serve as a quick way of verifying what you wanted to implement. Next, we can define our objective. And in GAMSPy, you don't have to use you don't have to define another equation for defining the objective. What you can do is you can just specify the expression into a Python variable, or you can even use this expression inside the model when you want to instantiate the model itself. So some right here you can use the expression again. And then again, we can now instantiate a model object. We again say the model would live in the container M. We give it a name, and then we specify the equations on which the model would be act upon. And in our case, it'll be the supply equation and the demand equation. The problem type will be a linear programming problem. And the since we want to minimize the objective, it will be minimization, and the objective will be the Python variable obj. And if I run this, and at this point, we have a mathematical model in the transport variable. There's another way of defining the model. And let's say in this case, we only had two equations for the model, but let's suppose we have multiple equations and you can't really write all the equations one by one in the list. What you can do is you can just call this convenience function get equations on the container itself, and it'll just return the list of all the equations which you have defined till this point and add it to the model itself. And if we run this, we'll have the same transport object. And now about the data. So once we have a model representation for our problem, we can start adding some data to it. Again, for the example, we have the Seattle and San Diego as the plants, New York, Chicago, and Topeka as a list of markets, and we can just set this into the set of market, which is the Python variable J. And similarly, we can set the capacities at each plant and the demand at each market. And we can quickly verify what we have set by using the records property on the variable I. And you can see, yes, the set of plants should have Seattle and San Diego in it. We can also combine the declaration and the data assignment in one step. So let's say in this case, now we want to define the distance matrix. So here we have a pandas data frame, and then we can directly say in the records that I want to set the records as a distance, or I want to use the pandas data frame as the set of records for my GAMSPy parameter D, which will be the distance matrix in my GAMSPy model. And if I run this, and now again, you can quickly verify the records in the GAMSPy parameter D. And you can see, yeah, yes, that's exactly the pandas data frame, which we defined over here. And then the last parameter which we want to add records to is the parameter C. And for that, we want to calculate the per unit transportation cost depending on the distance. And there are two ways of going about it. So we already have the distance pandas data frame. What we can do is we can calculate the cost, and this will be a pandas data frame again. And similarly, we can just add the records to the GAMSPy variable C or the GAMSPy parameter C by just using the set records method. And then again, verifying that yes, C.records have the necessary data, or since we already have the GAMSPy parameter C and the distance parameter D, we can directly use the GAMSPy assignment and populate the records in the parameter C. And if we run this, we get the identical result back. And now finally, we are ready to solve the model. And yeah, solving the model is as simple as just calling the method solve on your transport object. And if I run this, you can see the log over here, and this returns again a pandas data frame with some information. And we can see the solver status is normal. It's optimal global, that we found a global solution. So this is our objective value. There are 6 number of equations and 7 variables in this model. The model type was LP, and we use Cplex as the solver. And this is the default solver or default LP solver um, for GAMSPy. And like, what about like, how can we verify what we just solve? And for that, we can enable a couple of options. So if we just enable or specify equation listing limit to 10 and the variable listing limit to 10, because we had a total of 6 and 7 number of equations and variables. And if I run this again, now we'll have access to 2 convenience methods: get equation listing and get variable listing. What this allows to do, like if we call this on the transport object, we can inspect each equation in the model. So you can see there's the supply equation, the demand equation, and the objective itself. And you can have like the coefficients and everything is, you can verify the coefficients, the right hand side and the left hand side. We can call the get variable listing on the transport object again. And this time you'll see the variables in the model. So we just have the X variable and of course the objective variable, and you can see the coefficient in each equation for that variable. We can also use this convenience method on each equation or a variable. So for example, if I run this on an equation, supply equation, I just get the supply equation returned. And again, you can quickly verify that, yes, this is what I wanted to implement. Similarly, if I run the get variable listing on one variable, the X variable, now we just get the listing of the variable. And you can see that there is no objective variable in this listing. And then like, what about retrieving the results? Well, again, it's as simple as just calling the records property. And let's say I just want to access everything for the X variable. I can do that by running this. And if I want to access just the marginal, M is for marginal. And if I do that, I just get the marginals out of the X variable. And I don't know, if you want to get the level of the X variable, I can do so by specifying L for level. And similarly, if I want to get the objective value, I just use the property objective value on the transport object, and I get 153.675. Yes, now about the interoperability. If you want to convert your GAMSPy model into LaTeX representation, you can do so with this convenience function to LaTeX. Just have to specify where the file would be should be saved. And if I run this, this will produce the LaTeX representation of your GAMSPy model. And you can just copy this and paste it into an overleaf document, and you will have the PDF version of your GAMSPy model. And if you have the PDF LaTeX utility installed on your system, you can just change this parameter to true and run this again, and you'll have a local version, or like a PDF, local PDF of your GAMSPy model. Next, we can also quickly convert the GAMSPy model to GAMS. And again, for that, we can just use the convenience function to GAMS and just specify where the file should be saved. And if I do this, we can see it created this transport.gms file. And this is where it imports all the data. And this is the associated GDX file. And since we had solved the model, you can see that it also saves the level for that objective variable. All right. And the next about the post processing, and then this is where the Python shines, right? You can quickly use something like matplotlib to visualize your solution. All we require is some coordinates for your cities and the level um, of your variable. And then with that, and then some quick and dirty Python tricks, what we can do is we can plot our solution and have like a proof of concept. My solution is making sense, and this is what it looks like. And this is not a polished plot or anything, but yeah, this is just a proof of concept that you can quickly generate a plot in Python. And yes, if you want to change the solver, you can do so by just specifying which solver you want to use in the solver parameter. And if I run this, now you will see GAMSPy used IP opt-edge in the background and not Cplex as we did before. And finally, before leaving the live demo, I also want to mention if you want to install a new solver, for example, let's look at how you can view all the solvers. So GAMSPy comes with a command line interface with every GAMSPy installation, and you can list all the solvers which GAMSPy support with this command. And now you can see I have these solvers installed, and you can use, oh no, I think I have to run with A. And yes, and that lists all the available solvers which you can install. And then let's say I want to use highs to solve my model. Oh, I can just do GAMSPy install solver and then highs. And then I just mentioned use UV. And now we have highs available as a solver. And if I want to solve the same model again using highs, I can do that by saying transport dot solve. And then in the solver parameter, I just mention highs. And if you want to see the output, I pipe the output to the standard out. Oh, wow. And it's not installed. Oh, yeah, okay, because I need to restart the kernel. And let me run everything once again. Yes, and now hopefully we can solve our model with highs. And as you can see, it solved the model this time with highs. So it's really convenient to switch from one solver to another in GAMSPy. That's all I had for the live demo. Switching back to the presentation now. Yes. Yes. Okay. Now that we have a functioning model, let's take it to the next level by building a web application around it so that the end user can interact with it. We have our in-house solution, GAMS Bureau, for that, which is exactly that. We just have to define what and which symbols should be exposed to the user in the UI as input output. And with that information, Miro generates a symbol web application automatically. As you can see in this snippet, that I wanted to have the parameter d as an input and the variable x as a Miro output. I just change these two things, and what Miro does is generates this web application for me. And you can find this in the Miro library at this address. And then there is a configuration mode in the Miro application that allows to refine the application by choosing from numerous chart types, pivot tables, create dashboards, and etc. And since it is tightly integrated with GAMSPy, you do not have to do the heavy lifting while building the UI. But now that we are in Python land, it might be interesting to look at some Pythonic alternatives as well. This is where Streamlit comes into play. With Streamlit, you can control the UI as you like, since you build the entire application from ground up. And since the GAMSPy model is data agnostic, we can separate the backend, that is the model, from the front end or the UI. We have deployed the same problem as a Streamlit application in the Streamlit community where you can play around with it. There are also a couple of more applications in the same repository for you to explore. Again, we'll provide all the links at the end of the presentation. Now we can quickly look at the source code and the application itself. Yes. So let's first look at the model and what has changed this time. As you can see, the structure of the model is similar. The only difference is now I have wrapped the model in a function so that I can provide some arguments and some parameters, and I can change and can call this function and I can change the parameter as I wish. One key difference between that implementation and this is use of domain forwarding. So what this allows us to do, let's say I set this parameter A with my capacities data frame, pandas data frame, and GAMSPy will automatically take the domain from this pandas data frame and forwards it to the set of plants I. So at this point, like after this point, if you check what are the elements in the set of canning plants, it'll have the same records which were in the pandas data frame for for the plants. And similarly, for the parameter B, we can do the same thing and generate our set of markets by specifying that domain forwarding should be set to true. And apart from that, everything else is still the same. And again, you can see there is no data involved in it whatsoever. And in the main function itself, what we can do is, again, specify the same data and we can call the model. And if I run this, and if I run Python transport here, we can see, yes, we get the same objective value and the same level once again. Now we can also look at the Streamlit application itself. And this is, I just imported this function from my model, and that's all Streamlit requires. How you want to solve the model. It doesn't have to depend on GAMSPy at all. The Streamlit application itself, we just set some default values, and this is like a Streamlit specific thing, not a GAMS specific thing. We just specify some data, like a default data. Then we set some session states, like how it should start and how it should behave once we solve the model. And this is the main wrapper function, which wraps around this transport model, which we define in the other script. And we call this function with the same parameters, and we just keep changing if we want to change the data. And finally, we add some functionality to it, and we can change, like if you want to add more cities, we can do that. If you want to edit existing cities, we can do that. Or if you want to remove some cities, we can do that as well. And here I just calculate a Euclidean distance matrix out of some publicly available data set. And this is the function where I plot the solution found in a map, on a map. And in the main function, I just consolidate everything into one place and define the layout of my UI. And this is where we call the function. Let me solve transport. Yes, there we go. And this is where we actually call the function. So if we press the run optimization button, we just call the function. And we can also quickly look at the application as well. Yes, so and this is the finished product. And now if I say run optimization, it runs everything and you can see the solution. And of course, like the objective value is different because we had to calculate a different, use the Euclidean distance to calculate the distance matrix. But apart from that, the model itself was still the same. We can quickly add, let's add a new supplier and specify some capacity. We have to make sure, keep in mind that the demand is less than the capacity, the total capacity, so that it's not infeasible, so that our model is not infeasible. And with this new data, again, if I run optimization, and now it just solves the model with this new data, and we can quickly see, and everything is nice and proper. All right, now back to the presentation. Yes. Back to the presentation, and probably the most interesting part of the webinar, in my opinion. You may have come across use cases or papers or presentations dealing with different combinations of ML, machine learning, and optimization. And obviously, Python is the number one machine learning language with rich features and vast support of different machine learning libraries tailored to your needs. So with GAMSPy, we have great new options to interface optimization with ML libraries. Let us take a look at two core machine learning features that GAMSPy provides. First is the matrix interface. While algebraic formulation of constraints are usually the best choice when it comes to classical optimization models, in machine learning, there are cases where we need to deal with aspects of, let's say, a neural network. Example, a linear transformation done by a linear layer of a neural network. And there are the indices or also the equation defining that linear transformation have no physical meaning. So in that case, just using a matrix operation can be much more convenient. And that's what the matrix interface allows us to do. And secondly, we have GAMSPy formulations, which allows the integration of common ML constructs uh, and to add that into GAMSPy model. Now let us look at these two features into a little more detail. Yes, now earlier we would have to define two separate sets just to define this matrix. But now with the matrix interface, we can just use the a dim method out of the gamspy.math submodule to declare a matrix with dimension 10 by 20. We can also define another matrix, in this case, the matrix X with dimensions 40 and 10. And now that we are dealing sorry. And now that we are dealing with matrices, we can also do matrix multiplication. We can simply use the matrix product in our model equations using the at operator, which is of course much more convenient than writing this element wise. And if there is a mismatch between number of columns and number of rows, when multiplying two matrices, GAMSPy helps to detect problems early and throws a error with a descriptive error message, pinpointing the issue. On to the second core feature, with GAMSPy formulation, we provide support to embed construct that are common in machine learning, like tree-based models, certain neural network layers, activation functions, or just in general piecewise linear functions into GAMSPy model. Here we have an overview of currently supported most common tree-based constructs. As you can see in the snippet on the left, it becomes very easy and efficient to integrate a trained scikit-learn regression tree model into a GAMSPy model and solve the same using a MIP solver. The formulation call on line 15 returns the output variable for the embedded model and a list of equation governing that model. Similarly, here's a list of currently supported most common construct relevant in the context of embedding a neural network in an optimization model. In this snippet, you can see that again, how efficiently and elegantly we can embed a torch sequential model into a GAMSPy model. And GAMSPy generates all the intermediate but relevant variables and equations under the hood and returns just the output variable and the list of equations for that embedded sequential model. Also, the previous slide and this slide uh, is a moving target and will continuously keep on adding more formulations and construct to it. In addition to the formulation, GAMSPy also supports some commonly used activation functions when working with neural network. You can directly generate an activation function such as ReLU or hyperbolic tangent from the GAMSPy.math submodule. Example, when we, in this case, when we use the ReLU with binary variable, GAMSPy generates under the hood one binary variable, one positive variable, and three equations. Yes, now this was just a quick look at the capabilities of GAMSPy and what it can do with in the world of machine learning. If you want to learn more about this, we have another webinar planned where we dive deeper into this topic and unpack a lot more. We have some great use cases and examples which really showcase how optimization and machine learning can benefit from each other. And Mateo, if you want to add something to this.
Yeah, no, I'll just quickly jump in and say that, yeah, that was an interesting look at some machine learning capabilities within GAMSPy. So for those of you who are particularly interested in this section, we are planning a follow-up webinar on embedding neural networks into optimization models. And this session will be a much deeper dive, and it will specifically focus on how to integrate these more advanced machine learning techniques directly into optimization workflows. So we will be putting out all the details in the coming weeks. So just keep an eye on our website and on our LinkedIn, and we'll make the official announcement soon.
Perfect. And finally, we can answer the question once again of why you should start incorporating GAMSPy in your workflow. If you want to start using GAMSPy, it is installing it is as easy as running pip install GAMSPy in a terminal. We have already released a stable version. You can find everything about GAMSPy in the up-to-date documentation. And if you want to scroll through some models and look at some examples, you can look into the model library where we have 100+ models. We already saw about the solver independence, how easy it was to change from CPLEX to IP optech by just specifying which solver we wanted to use in the solve statement. We also saw data independence through the Streamlit application, that we could just change the data as we wanted, as compared to some other library where we have to start with the data and build or like define the model itself around the data. Around the data. And again, the convenience, as we saw in the case of the matrix interface, here as well, if we look at the line 13 where we define the demand constraint, let's say instead of specifying xij, I specified xjj. And because in GAMSPy, everything is defined over set, so it's everywhere it's logically consistent. There can be no domain violation. And since on line 13 there is a violation, GAMSPy just generate a validation error early on with a helpful error message specifying that you should not use set j at that location and just use set I, because that's what's the declared domain for that variable. And that's the GAMS philosophy in a nutshell. Tight syntax leads to better modeling. And now, considering all the other properties, it does not mean that we are sacrificing the performance. As you can see in the plot, the difference between the performance of GAMS and GAMSPy in generating large sets with hundreds of thousands of indices is small. You can read more about this analysis in the blog article, where we compare the performance of GAMSPy with other libraries. And we also looked at interoperability, how easy it was to translate a GAMSPy model into LaTeX or back to GAMS, or how easy it was to generate a UI interface using Miro. And if you want to solve your model on cloud or on-prem using a centralized resources, we have another solution called GAMS Engine. You can look into that. And again, it's really easy to make this connection between GAMSPy and Engine. Quickly summarizing the key points once again, GAMSPy generates mathematical model and not instances. They are pure representation of mathematical symbols and devoid of any specific data. GAMSPy gives you access to a broad set of state-of-the-art optimization solvers. It provides this unique and streamlined way of completing tasks like pre and post processing and visualization all in a single environment. GAMSPy works seamlessly with GAMS Miro, GAMS Engine, and NEOS, which provides you to solve the model either locally or on remote servers. Once again, GAMSPy is fully installable with one line, pip install GAMSPy. All right, that's all I had to say for this webinar. I hope you find this session productive and insightful and would be willing to give GAMSPy a try. I would like to give it back to my colleague, Mateo, who will talk about the academic program.
Yes, thanks, Vijay. So hello again, everyone. I also hope that you found that demonstration insightful and that you are already starting to see the potential of integrating GAMS with Python into GAMSPy for your work. Now I'd like to take just a few minutes to tell you about our academic program and how we try to support the academic community. So all of the information I'm about to share can also be found on our website at gams.com/academics or by scanning the QR code on the screen. And then again, we can also share these slides via email after the webinar. So if we go to the next slide, no, sorry, back to the previous one. Yeah, yes, perfect. So at the heart of our academic program is a free licensing scheme. So if you're a student, professor, or researcher, you can head to our website and get a free GAMSPy license directly there. And the process is really very simple. These licenses are valid for 12 months. They are completely renewable. They come with no model size restrictions, meaning that you can solve problems of any type and any size. And most importantly, they include full access to all available open source solvers and even to multiple high-performance commercial solvers like Cplex, Mosaic, Copt, Conopt, and even Gurobi. This is really a big advantage because it means that you can do your research or your teaching using professional industry standard tools completely for free. So now, yes, if we go to the next slide, just wanted to mention that beyond the free licenses, we also have a very active community forum, which is a great place to ask questions. So if you're ever stuck with a problem, you don't know how a feature works, or you get an error and you don't know how to solve it, you can just post the question in the forum. And because it's quite active, you will probably get an answer from an expert rather quickly. So just check it out, share your questions, and take advantage of it to connect with other optimization experts. Our YouTube channel has numerous tutorials and new videos on GAMSPy are coming up, so you can also check that out. And then I would also encourage you to read our blog posts and case studies just to see how optimization and GAMS are used to solve real-world problems in various industries. And this is something that I think is interesting, especially to share with students, so they can see how the leading players in many industries actually use optimization and GAMS in real-world problems. Then for those of you who are interested specifically in building web apps, we do have, as Vijay mentioned, a Streamlit library that is available on GitHub. And finally, we are very excited to announce a new student competition, a new GAMSPy student competition. We had one last year that you can read all about in our website, and it featured really impressive submissions. I would like to give a big shout out to the University of Wisconsin-Madison that took first and second place, and to the Missouri University of Science and Technology that took the third place. So stay tuned to our LinkedIn and our website for all the upcoming details about this new student competition. And now we will move on to the Q&A session where we will address some of the questions. I saw that Muhammet has been answering some of them as we were speaking. But if you have any pending questions, please post them on the Q&A chat down here, and we will try to answer them. Let's see if we have anything pending. Okay, I see that most of the questions have already been answered. Okay. There's a new question. Of course, if there's anything too complicated, you can just post it on our forum, and then you can get a proper answer. Then we won't go into very deep questions here. Okay. If there's anything else. Okay, then I guess that's it for today. I would like to thank again everyone for joining us today. We hope that you found this session valuable and that you're basically excited to explore all the possibilities that GAMSPy has to offer. If you have any remaining questions, which you might have, please feel free to reach out to us at academic@gams.com. And I also recommend that you subscribe to our newsletter just to stay up to date with the latest news and the upcoming events. So thank you all for your time and for your interesting question. And with this, we will conclude our webinar for today.
Thank you. Thank you, everyone.
Thank you very much.